Hello everyone, this is the presentation for the enhanced convex hull based clustering for high population density avoidance and the D2D enabled network research paper which was accepted by VTC 2021. My name is Vishaka Basnayaka. The co-authors are Professor Hakim Marbet, Professor Philippe Canalda, and Professor Dushantha Nalin Jayakwadi. The main focus of this work is to find the localization of population congested areas in the local networks. So let me first ask you a question. What mainly causes the spread of pandemics such as COVID-19, Spanish flu, etc.? High population congestion is shown to be a major factor in spreading the disease. It had been shown that in sparse environments, the the fraction of infected people is lower over the time when compared to a crowded environment which has a higher fraction of infected people over the time. What are the ways to access reliable information of the most crowded areas? Wireless communication and positioning technologies provide a significant support in this aspect. For example, aerial vehicles such as drones provide application services such as surveillance, delivery of services, aerial mapping, and so on. Also, localization of population clustering is possible using unsupervised learning methods. Let me introduce you the service architecture proposed in our work, which is Enhanced Population Clustering or EPC. In this service architecture, an aerial vehicle is providing services to devices which are in a local network. The devices can either be in coverage at the edge or in the out of coverage regions. The aerial vehicle is providing the information of the most population congested areas in the region. So, the mobile user devices who have subscribed to the service establish a device-to-device link with the aerial vehicle. The device-to-device link is established according to their coverage status. If the devices are in coverage, they use the authorized D2D resources to connect with the to establish the communication link. And if they are out of coverage, they use random D2D resources and use synchronization signals such as primary synchronization, secondary synchronization, and synchronize the devices before the communication of data. After the establishment of the communication link, location of the mobile devices are updated to the aerial vehicle at TW time intervals. The aerial vehicle is storing the data for a maximum time period of T0, and it computes a parameter called request rate during a time interval of Tm. Using the RR parameter, a suitable clustering mode is selected, and after that, cluster centers are localized under 3 steps. The 3 steps which are used are convex hull computation, maximum volume ellipse optimization, optimal cluster center computation. After all these steps, after finding the cluster centers, the cluster center locations are updated with the mobile user device. At the initial moment when the user device is requesting the cluster center locations, the previously computed cluster center locations are updated to the device. And once the the computation at the aerial vehicle are done at TW time intervals. They are updated back to the user devices in the second and the third times. In the initialization process, I mentioned before, I will explain further the initialization process using more information. So after storing the data for a T0 maximum time period, the aerial vehicle is computing NTW and RR parameters. NTW means the total number of requests divided by the fixed time period TW. So RR request rate is computed using the average of NTW measures divided by the TM time period. TM is the time used to calculate the RR rate. RR rate is an representation of the average number of requests received over a unit time. So if the number of requests received are high or it is above 1, the periodic clustering mode is selected. The periodic clustering mode is periodically computing the cluster centers and communicating to the devices. However, if the request rate is low, then we are selecting the only one clustering mode, which is computing the cluster centers only once new requests are received. So at the initial state where the mobile user device is requesting the locations, the previously computed cluster centers are updated back to the user device. The cluster centers are localized under 3 steps, as I mentioned before. The convex hull of the data points are computed, and the convex hull is determined by A and B parameters, where determined by line segments, which are determined by the A and B parameters. The second step is the maximum volume inscribed ellipse optimization. The ellipse is defined using this equation, where beta and d are deformation matrix and orientation of the ellipse respectively. So the ellipse which fit inside the convex hull is defined using this constraint, and the volume of the ellipse is defined using this equation. And it is possible for us to find the maximum, the ellipse with the maximum volume inside the convex hull. So what is the importance of finding this maximum volume inscribed ellipse? So this is the novel aspect of our work. The ellipse which is included in this convex hull is used to provide a boundary between the more clustered areas and the less clustered areas. As it is seen, the data points which lie outside the ellipse are more scattered than the data points which are inside the ellipse. The maximum clusters are situated inside the maximum volume ellipse. Therefore, it is more convenient to focus on the data points inside the ellipse to find the optimal number of clusters in the area, which help us to find the optimal number of clusters using a lesser number of data points. The gap static method is used to find the optimal number of clusters in the inside the ellipse. After running the gap static for a fixed number of times, the iteration which gives the maximum gap static score is used to find the corresponding optimal number of clusters. After finding the optimal number of clusters, that count is used to detect the clusters in the total data points. And the quality of the clusters detected is found using the Silhouette score. Silhouette score is a representation of how much the clusters which were detected are separated. If the Silhouette score is a high value, then the clusters detection is performance is good. So Silhouette score is defined using this equation, and it is found using the sum of Silhouette score at each data point divided by the total data points. The Silhouette score at each data point is found using this equation. BP and AP parameters are AP is the mean distance between P and all other data points in the same cluster. BP means the mean distance between P and all data points in the nearest cluster. Data size reduction is the other parameter. It is the total number of data points minus the number of data points inside the ellipse. In the gap static method, we use this data. We achieve this data size reduction when computing the optimal number of clusters only using the data points inside the ellipse. In implementing the performance of the EPC, we use 100 to 100,000 devices, and we assume that the clusters are following a Gaussian distribution. And we compared the performance of our proposed algorithm with the conventional K-means and Gaussian mixture model schemes. And it was seen that the proposed architecture was able to improve the conventional cluster performance, and the percentages of improvement are given in this table with respect to K-means algorithm and the Gaussian mixture model. And also, according to the different environment types, the performance of the EPC was compared with the conventional cluster methods. This table gives the average improvement possible by the EPC compared to K-means and Gaussian, and also the data size reduction possible under each environment type are given. And in average, 18.93% of improvement is possible by the proposed approach compared to the conventional clustering methods. Also, data size reduction of 15% is possible in general with respect to all the different environment types. Now let us focus on the contributions of this work. This service architecture is accessible by wireless devices which are in coverage edge or in the out of coverage areas. We proposed a service architecture which can deliver the cluster center locations reliably to the user devices. Also, it was shown that the quality of the cluster detection was improved by the proposed approach by 18.93%. And the cost efficiency was improved because we allowed a 15% of data size reduction. As for the future work, the performance of the EPC can be analyzed under different other distributions of population that follow other distributions than Gaussian. With that, we come to the end of the presentation, and thank you.